Hello everybody, my name is Yannis Koutromanos. I'm an associate professor at Virginia Tech. The presentation I'm going to give titled Multiphysics Simulation of Chloride-Induced Corrosion Damage in Concrete Bridges involves work that I have done with my former PhD student, Mojtaba Aliasghar. He's currently a postdoc at UT Austin, and also my colleagues Karin Roberts-Wallman from Virginia Tech and Matthew Hepton from UT Austin. Before proceeding, I would like to apologize for being unable to give this presentation in person. Hopefully it will still be, let's say, kind of a rewarding experience for the audience. So let us begin with some introductory remarks. Corrosion in concrete bridges is one of the predominant reasons for the long-term deterioration of bridge infrastructure. Here are some example photographs from actual bridges located in Virginia which exhibited, let's say, severe, if I can use the term, visual corrosion damage. The capability to describe and predict this phenomenon is, of course, crucial for the decision-making on the maintenance and repair of bridges nationwide. Now, corrosion is caused by intrusion of chloride ions due to seawater spray in coastal bridges or use of de-icing salts, and of course it is a complex phenomenon. It involves a variety of different processes which are interacting with each other. So, for instance, we have the chloride transport being affected by both advective and diffusive transport mechanisms and also by the temperature. Chlorides themselves then lead to an electrochemical oxidation reduction, that is, reaction. The corrosion products of this reaction, the iron oxides, let's call them, have an increased volume compared to the original material. And this increased product volume causes tensile stresses and cracking to occur in the concrete surrounding the reinforcing or pre-stressing steel that undergoes corrosion. And of course, the occurrence of cracking itself can further accelerate and exacerbate the future chloride ingress and the corrosion process. Now, it's the complexity of this phenomenon that renders it a good fit for application of machine learning algorithms. And indeed, I have some example slides here involving an ongoing study of ours focused on the use of machine learning for determining the chloride content in concrete components. We have a data set for the training and validation of our machine learning algorithms, consisting of a total of about 900 measurements from experimental tests, which allow us to deduce, let's say, first of all, the correlation between the chloride content and also some key features of the concrete member. And also I have some example application of a machine learning approach, specifically what we call a voting regressor algorithm, combining being itself a combination of different approaches, namely what we call the lasso approach, the multiple layer perceptron artificial neural network, support vector machines, random forest, Gaussian process regression, and also extreme gradient boost. And it turns out that if we calibrate, let's say, with a subset of our data, then we can obtain very good capability to predict the remaining of the test data. And also we can even obtain quite good estimates of distributions of chloride content with the depth from the surface of the concrete member. So if this works so well, what could be the problem? Okay, well, the problem, which is what constitutes the motivation for the remainder of this presentation, is that while these machine learning algorithms are indeed very promising, there are at present several limitations regarding their efficient use. First of all, the available experimental data on which the previous slides eventually relied do not cover a sufficient time interval that would compare with the actual life cycle of real-life bridges. Also, the available of these experimental data do not consider the real-life exposure and ambient environment conditions for actual bridges, and also all the interactive phenomena of interest. Okay, which of course means that analytical simulation is probably necessary to allow us to obtain reliable data for the efficient training and validation of machine learning tools. Which brings us to the core topic of today's presentation, which is a framework that we created for the simulation of corrosion damage. It's basically a set of multiphysics mathematical models describing chloride ingress and corrosion. It has been implemented in a finite element code, calibrated with experimental data from material tests, and then used, as I'm going to demonstrate towards the end of my presentation, for analysis of real-life bridge girders that experience corrosion damage after decades of service. And this particular simulation scheme also enabled various interesting investigations, for instance, the evaluation of simplified design-oriented equations, and also the uncertainty quantification for some key decision variables, for instance, the anticipated corrosion initiation time for the pre-stressing strands of a given girder. So let's begin with an overview, a schematic overview of the mathematical model and problem setting that we are considering. So we have a three-dimensional domain, or a multi-dimensional domain in general, which constitutes our bridge girder, which then involves various interreacting processes. So we have heat transfer, moisture transport, and then chloride transport, both diffusive and advective. The latter is affected by the moisture itself. We have this domain being exposed to various ambient environment, let's say, conditions, so an ambient temperature, an ambient relative humidity, and also an ambient surface chloride content. And also we have exposure to solar radiation. And of course, the interaction with the environment is conducted through the bounding surface of this particular domain by virtue of appropriate, let's say, mathematical conditions. Another aspect which of course is included in our mathematical model is the mechanical damage itself, specifically cracking in the concrete, and its interaction with the other non-mechanical processes, heat transfer, moisture transport, and chloride transport that I mentioned here. So about our mathematical model, I'm going to quickly glance through the equations. For the moisture transport, we have a differential equation basically, where the field variable is the relative humidity. We have various parameters which are established on the basis of previous work in the literature. For instance, we have a so-called Van Genuchten sorption isotherm, and also we have an apparent moisture diffusivity coefficient relying on earlier work of Bazant and Najjar, and also having the capability to account for the impact of cracking on the moisture transport properties of a concrete body. We also have appropriate let's say, differential equations to describe time-dependent heat transfer, where the field variable is the temperature, of course, and also chloride transport, with the field variable being the chloride concentration. Now, chloride transport involves diffusive transport, which is primarily governed by this diffusion coefficient, given by this extremely simple formula, which, okay, long story short, involves both the effect of temperature and the effect of cracking. Both of these are important effects. And also, apart from diffusive transport, we also have advective transport of chloride accounted for by our governing equations. This advective transport is, of course, governed by the moisture flow velocity. Now, corrosion and concrete cracking are also accounted for in our model. The rate of electrochemical corrosion is determined on the basis of a so-called Evans diagram. I'm not going to enter into much detail, but we have so-called polarization curves corresponding to the anode and cathode of these diagrams. The anode is basically the steel bar or strand that undergoes corrosion, and we have the impact of increasing chloride content on this diagram accounted for. This diagram eventually provides us with the corrosion current density value, which subsequently is converted to an iron oxide, let's say, chemical reaction production rate through Faraday's law. Then once we have this rate of oxide production, we also have a formula that describes the expansion of corroded steel, and ultimately concrete cracking itself is described through use of a smeared crack constitutive model formulated by Moharami and Koutromanos. Now, the finite element implementation and solution of this mathematical model is implemented in our in-house research code, FE Multiphys. We employ a nonlinear static solution for the stress and deformation part of the computation, an implicit backward Euler scheme for the integration with time of the equations governing heat, moisture, and chloride transport. And we also employ an iterative, specifically a Newton-Raphson procedure to satisfy the governing equations at each step of our time marching analysis. One other note is we also employ SUPG streamline upwind Petrov-Galerkin stabilization for the chloride transport solution to prevent so-called spatial instabilities which may occur for advection-dominated cases, or if you prefer, for situations involving high Pechle numbers. Now I'm going to quickly glance through the calibration process. So basically we have calibrated each and every aspect of our mathematical model and its associated numerical implementation. Here are some example calibration analyses that we did with experimental test data involving heat transfer in concrete. We also did calibration with experimental data involving moisture transport. I'm trying to quickly glance through them. And then we also had calibration involving the chemical diffusion coefficient for concrete for different temperature values. Also, the corrosion kinetics themselves were calibrated using test data available in the literature, specifically a study by Hussein and Isida. And finally, we also calibrated the corrosion-induced cracking aspect of our model, so the mechanical computation and its coupling with the corrosion kinetics by virtue of, leveraging material test data by Molina et al. And also Cabrera. And finally, of course, we also did calibration studies involving the impact of cracking on the chloride diffusion itself. So again, we did additional calibration analysis, which I'm not going through here, just to save as much time as possible. Now, having conducted the calibration of our modeling scheme, we proceed, let's say, to the validation analysis. That is, how confident are we that if we use this for the prediction of the behavior of a real-life bridge, we will obtain, let's say, accurate reproductions of what happened in real life. So to this end, we resort to two damaged prestressed girders taken from actual bridges in Virginia after decades of service. So we had an I-beam, an I-section beam, taken from a coastal bridge it was decommissioned after 49 years of service, and we also have a box beam which was taken from a bridge away from the coast after 34 years of service. Both these bridge beams involved 7-wire strands, which, as we will see in subsequent slides, some of them had severe corrosion damage. And what we did in our lab was chloride titration tests to determine the chloride content at different depths from the surface of these concrete beams. Now, one additional remark that I want to make is that these beams were kept stored. The I-beam was kept stored for 2 years after its decommission before the titration test. The box beam was kept stored for 6 years before the titration test. And as we're going to see, these had an impact on the measured chloride content as deduced from analysis. Now, the girders exhibit visual corrosion damage in the form of cracking and spalling in the concrete, especially in the vicinity of corner regions in the section. So this is a close-up of a particular corner region in a section in the I-beam section. And also, if we do a close-up here of the strands, you can see how badly some isolated strands were damaged due to the corrosion effect. The analysis was set up in such a fashion that the applied boundary conditions were representative of the actual climate data in the vicinity of the two real-life bridges as obtained from weather stations. So we had weather station data which allowed us to obtain time histories of ambient temperature and also relative humidity over a representative 1-year interval, and then we basically applied these same exact boundary conditions in a periodic fashion throughout the entire lifespan of each bridge. The surface chloride that we considered as an ambient condition was based on recommendations from the literature, and also the removal of the beams from the actual bridges and their storage prior to the titration test were explicitly accounted for in our analysis. So here I have some sample analysis results, first starting with the I-beam. So on the left I have the maximum principal strain contour, which indicates the crack formation and propagation. On the right I have the evolution of the total chloride content in the interior of the section, so it becomes apparent that this girder, indeed the analysis of this girder predicts the gradual formation of extensive cracking due to corrosion in multiple strands, and also the cracked regions constitute pockets of, let's say, increased localized chloride ingress. A similar conclusions are reached for the box beam analysis, where once again these are close-ups of the bottom, let's say, flange, the bottom face, or in the vicinity of the bottom face of the box beam section. And again, we can see on the top the gradual formation and propagation of corrosion-induced cracks. And also at the bottom, it can be seen that the crack locations constitute pockets of increased chloride ingress. Now, more important question is, okay, how well can we match real-life measurements? And to determine this, we can see that the analysis gives distribution of chloride with depth at the end of the service life and during the titration test that we did. Remember, its beam was stored for several years before the tests were done, for several years after the end of service. So these are our actual measurements for the I-beam, okay, at different phases, let's say, and it can be at different locations, let's say, and at different, and we have distributions of chloride content with depth, and it can be seen that our analyses were able to quite well reproduce the experimental measurements from the titration test. Also, they do indicate the significant effect that the storage process was expected to have on the actual chloride distribution with depth. Okay, we have the similar measurements and associated analysis results for the box beam, where again we have a similar set of findings and conclusions. Now, the analysis results also enable the evaluation of accuracy in design-oriented procedures. For instance, here I have an example evaluation of the accuracy of the procedure in the FIB code, specifically the bulletin 34 by FIB for determining chloride content. And in general, our findings indicate that, okay, here we have different time histories of chloride content at different locations of the section for the I-beam and the box beam, at two distinct strands. One is near the corner of the section, the other is away from the corner. In general, we reach the conclusion that the simplified procedure in the FIB bulletin tends to rather underestimate the chloride content evolution with time. Another important question that we were able to infer from our analysis results is the impact of cracking itself on the corrosion evolution. So here we have a close-up in the vicinity of the corner of the I-beam section, and we see the chloride content contour plot in the vicinity of the corner of the section for the case that explicitly accounts for cracking, and then for an analysis which does not involve the effect of cracking. And it can be seen cracking has a significant impact on what chloride content is actually experienced by different strands in the vicinity of the corner. More importantly, it turns out that the evolution of normalized strand area loss for this corner strand actually is very, very different depending on whether we account or we do not account for cracking. So the inclusion of the cracking effect leads to a significant acceleration of the sectional area loss in this strand due to corrosion. Now, the final aspect that I wanted to mention is a probabilistic study that was actually also enabled by our analytical tools. This is a study which essentially relied on what we call a stochastic collocation approach. And long story short, what we are able to obtain is, let's say, probabilistic descriptions of some important decision variables. For instance, the chloride content in the I-beam. Okay, so these are the cumulative distribution functions of chloride content for a strand near the section corner, obtained at different ages for our particular I-beam section, obtained from actually thousands of analyses that we conducted. And these are the corresponding cumulative distribution plots for the total chloride content for a strand away from the section corner. A more important, let's say, probabilistic decision variable that may be of interest is what is the probability of initiation of strand corrosion for a given bridge. And it turns out that we are also able to reach, let's say, results pertaining to this particular question. For instance, this is a plot involving the probability of corrosion initiation for two distinct strands. One is away from the sectional corner, the other is near the sectional corner at different ages for the I-beam, and then the corresponding plot for the box beam. So these are important, let's say, decision variables that are, of use to actual, for instance, bridge owners regarding the maintenance and repair decision-making schedule for bridges. So before closing, some concluding remarks that I want to provide. First of all, machine learning algorithms can indeed provide predictions of chloride distribution consistent with experimental tests, but at present their capability may be hindered by the lack or inadequacy of experimental data to enable learning throughout the entire structural life. And this is where high-fidelity multiphysics models come into play and become relevant and potentially necessary, since they have the predictive capability to enable the efficient training and further validation of machine learning algorithms for different structural configurations and ambient conditions. And before closing, I would like to once again thank you very much for your attention and patience. Once again, I would like to apologize for being unable to give the presentation in person. And in case you have any questions or comments, or simply want to reach out to me with some outcry for my absence, please feel free to do so by contacting me in my email address. So once again, thank you very much for your attention, and I hope this has been a rewarding presentation. Thank you.